video course Introduction to Flow Mechanics. My name is Matti Ylitalo and I'm your teacher during this course. Today our topic is convection, and by definition convection means heat transfer that occurs because a movement of fluid. Fluid can be liquid or gas, but movement is the key factor when we are talking about convection. So convection means that we are carrying heat from one place to another place. And there are two different types of convection flow. First, this natural convection or free convection, which is caused by density differences. That's the main mechanism to create motion in, for example, in the atmosphere and in seas. One example that is that warm air is rising from a hot plate or hot body. Another type of convection flow is so-called forced convection. When we are talking about forced convection, we always have an external force that creates the fluid motion. The force can be, for example, a fan or a pump, depending on case. Here we have many everyday examples of forced convection. For example, a sailing fan or table fan that's carrying heat away from your skin. That's forced convection cooling. Hair dryer is another good example. It's blowing heated air over your hair and creates forced convection, which enhances evaporation. There are many good examples also in car industry, and for example your computer cooling fan is a very good example of forced convection. Inside your laptop is a small fan that creates airflow and cools down those components inside your laptop. In industry, typical examples of forced convections are heat exchangers. We use pumps and fans to force fluids go through those units. On the right side you see a schematic picture of a heat exchanger. We can have, for example, cold airflow in inner pipe and hot airflow in outer pipe. Then we have forced convection on both sides of that inner tube. But there is also, of course, heat conduction through this wall material of that inner pipe. A typical industrial example is also electronic cooling by liquid cooling loops. Then we use pumps to move this coolant go through those microchannels of processors and power electronics. A very important application of forced convection in engineering is flow over a flat plate. And that's because in that case it's quite easy to measure the temperatures and velocities above the plate. And our next topic in this video will be that we will learn how we can calculate the heat transfer from a plate. Let's have a look what happens when we have flow over a flat plate. Here in this picture we see a flat plate and we have an even velocity profile coming from the left in this picture. And because our plate is fixed, it's not moving. It means that at the surface of this plate, the velocity of the fluid must be 0. And we define our boundary layer thickness so that it is distance from the surface of this plate at which we have the fluid velocity 99% of the incoming free stream velocity. It means that this boundary layer thickness is increasing when we measure distance from this leading edge of this plate. If we have temperature difference between our plate and incoming fluid, we will have also temperature boundary layer. We define this thickness of temperature boundary layer so that it gives us the distance from the surface of the plate to location where this temperature difference is 1%. This temperature boundary layer is also increasing when we measure distance from the leading edge of our plate. When we develop calculation methods for this kind of cases, we typically separate laminar and turbulent zones. And that's because in turbulent zones we have a lot of small eddies which increase the mixing. And the heat transfer there is totally different compared to laminar zones. And we use so-called Reynolds number to say when the flow is laminar or when it is turbulent. And this Reynolds number is fluid density times fluid velocity times characteristic length and divided by fluid dynamic viscosity. And if we are calculating a flat plate, our characteristic length is the measure from the leading edge. And for pipe cases we use pipe diameter. For airflow over a flat plate we can say that it's laminar if the Reynolds number is below 3 times 10 to the 5th power, and it's fully turbulent if this Reynolds number is higher than 5 times 10 to the 5th power. Here are some guidelines how we can estimate the thickness of a thermal boundary layer if we know the thickness of a velocity boundary layer. This experimental result is saying that the thermal boundary layer thickness is proportional to velocity boundary layer thickness times the Prandtl number to the power of negative 1/3. For example, for air, this thermal boundary layer is slightly thicker than velocity boundary layer. But for water, thermal boundary layer is thinner. And if we have liquid metal, then this Prandtl number is very, very small, and thermal boundary layer is much thicker than this velocity boundary layer. There is a very long history in this boundary layer research. Even more than 150 years ago, many studies were done. I wanted to raise up one study It's this Reynolds analogy. It's still used in many models, and it's saying that there are similarities between friction and heat fluxes on the surface. And the benefit of this analogy is that if we have measured values for friction, we can calculate heat transfer. And we need to know those similarity coefficients, but it's much more easier to measure friction compared to measure heat transfer. To calculate the boundary layer thickness for laminar flow, we have a very simple function here. It's saying that the boundary layer thickness is proportional to distance from this leading edge divided by square root over local Reynolds number. And as an example, if we have air velocity 1 meters per second and we want to calculate this boundary layer thickness at location 1 meter from leading edge, we will see that the boundary layer thickness is 1.9 centimeter. This is a typical value for boundary layer thicknesses. We are talking about millimeters and centimeters. Here is shown how you can calculate the drag force. The drag force is coming from shear stress, and that's coming from viscous friction. And to get this drag force, you need to integrate this shear stress over this plate surface area. And here you have a function how you can calculate that for laminar flow case. And if you have a turbulent boundary layer, you can use this surface friction average coefficient. And here is the summary table how you can calculate this drag force for laminar and turbulent cases. How we can calculate heat transfer from a flat plate? That's what we often need, and we already know that the heat flux is heat transfer coefficient times temperature difference. The temperature difference is of course the temperature difference between our flat plate and environment. But because we now have this boundary layer development, there are some differences if we have constant heat flux or if we have constant temperature. And typically when we are talking about heat transfer calculation from flat plate, we use so-called Nusselt number. And it is heat transfer coefficient times the distance from this leading edge divided by fluid thermal conductivity. And here we can see local Nusselt number for constant wall temperature case and for constant heat flux case. And there is difference in this constant value. Here we have average Nusselt numbers calculated over the length of the plate. If we have a turbulent flow, then the difference between constant wall temperature case and constant heat flux case is very, very small, and we can use same function for Nusselt number for both cases. Here are some details why we have these differences between our cases. If we have a constant wall temperature, then at the leading edge we have maximum temperature difference, and that creates steep gradient. But if we have a constant heat flux, then our wall temperature is increasing with distance from this leading edge. If we have a turbulent flow, then we have that strong mixing in a boundary layer, and that affects so that both thermal boundary layer and velocity boundary layer behave similarly. And the local temperature distribution in the wall is much less sensitive whether we have this fixed wall temperature or constant heat flux. Let's take a simple example. In this case we have a horizontal flat plate and we have a uniform velocity coming from the left and uniform temperature, and we want to know the thickness of our boundary layers. I asked a Python code from ChatGPT and calculated this example case. The velocity is now 1 meter per second and the length of the plate is 2 meters. And in this picture we see the thickness of our velocity boundary layer. It's this black curve, and seems that for example at 2 meters the thickness is almost 30 millimeters. And the thickness of the thermal boundary layer, if we have air, is seen on this blue curve, and it seems that at that location the thickness of thermal boundary layer is around 30 millimeters. And if we have water flow, we will have the thickness of boundary layer around 15 millimeters. So it's much thinner compared to air case. If you are reading a publication, you can meet a so-called Stanton-Colburn analogy. It's saying that if you know the friction factor, you can calculate the heat transfer. Here is a function from which we can calculate this Stanton number, and this Stanton number is a function of heat transfer coefficient. So if you know friction factors, you can calculate always heat transfer coefficient. That's the benefit from this analogy. So far we have been discussing boundary layer development on the surface of the flat plate, but there is this same phenomena also in pipe flows. Here we see an example when we have flow entering a pipe. When the flow goes inside the pipe, the boundary layer starts to develop around the periphery of the pipe. And after some length, which we call entry length, the boundary layer thickness is the same as the radius of the pipe, so the boundary layer meets in the middle of the pipe. And here we have a function from which we can calculate this entry length for laminar case. It's a function of a Reynolds number. In this case, when we are calculating pipe flows, we use in Reynolds number this average velocity and pipe diameter. For turbulent flows, this entry length is typically around 10 times the diameter of the pipe. When our flow is laminar and when it's turbulent, we can estimate it from this Reynolds number. And when calculating this Reynolds number, we use this average velocity and this pipe diameter. And if our Reynolds number is less than around 2300, we can say that the flow is laminar, and then this velocity profile is almost parabolic. When this Reynolds number is higher than around 4000, this flow is fully turbulent. Typically, then this velocity profile is more flat. If we need to calculate the boundary layer thickness in this entry zone, we can use the same function as was used for our flat plate case. It is having this distance from inlet of the pipe, and this Reynolds number is calculated based on that distance from inlet. But in this pipe case, this boundary layer thickness cannot be higher than the radius of the pipe. If you need to calculate the velocity profile in pipe for laminar flow, you can use this simple function. Here this U max can be calculated based on your volume flow and cross-sectional area. If you have a fully turbulent flow, then you can use this power law function to calculate the profile. Here in exponent we have this n, and for air and water you can use n is 7. If the wall of the pipe is heated, then we will have also thermal boundary layer and thermal entry zone. And for laminar case we can estimate the length of that zone from this function. And for turbulent flow, the length of this zone is around 10 times the pipe diameter. When you need to calculate the heat transfer coefficient for the turbulent pipe flow, you can use this function. Here in Prandtl number you have exponent n, and you can use 0.4 for heating case when the wall temperature is above the free stream temperature, and 0.3 for cooling case. And when you know this Nusselt number, you can calculate the heat transfer coefficient when you know your fluid thermal conductivity and your pipe diameter. Effect of roughness can be quite remarkable. The effect of roughness depends on what is the height of those roughness elements. If the height of those elements is so small that they affect only in so-called viscous sublayer, then the effect is very small and we can neglect it. But if those roughness elements affects on our main flow, then the effect on heat transfer and pressure drop can be quite remarkable. Typically we analyze the effect of roughness using so-called K plus value. K plus is a function of a so-called friction velocity, height of the roughness elements, and kinematic viscosity of the fluid. On the right side you see a guideline how you can calculate this friction velocity. If you have laminar flow, then this friction factor is a simple function of a Reynolds number. But if you have a turbulent flow, then you need to iterate to get this friction factor. And When you calculate this K plus value and it's below 5, then you can say that the surface is smooth. And if this K plus is higher than 70, then it is fully rough. Here we have some kind of a summary how this roughness affect on flow. If this K plus value is less than 5, we can say that the roughness has no effect on friction factor and Nusselt number. But if this K plus is higher than 70, then this friction factor becomes nearly independent of Reynolds number and heat transfer is enhanced. In industrial cases, we can say that all polished components are smooth. But in some cases, for example, contamination and corrosion can create these kind of roughness elements, which can have a big effect on heat transfer and pressure drop. Typically in heat transfer units, the roughness enhanced heat transfer, but it affects on pressure drop so that the pumping power is high. Many times you need to calculate the pressure drop in a pipe flow, and here is a simple function how you can calculate that pressure drop. It has this friction factor, pipe length, pipe diameter, fluid density, and the mean velocity of fluid. And in case of laminar flow, this friction factor is a simple function of Reynolds number. But in case of a turbulent flow, you need to iterate to get this friction factor. You can also use so-called Moody chart. It's shown here on the right side. On the x-axis we have Reynolds number. On y-axis we have this friction factor, and there are different curves for different relative roughness. This relative roughness is the height of the roughness elements divided by diameter. You can take this friction factor from this chart or calculate it. If you have pipe bends or pipe expansions or valves or something like that, you will have local pressure losses, and you can calculate those pressure losses using this simple function. It has a K value times this density of the fluid times the velocity of the fluid, and these K values you need to find from tables or internet. For example, this is a good reference from which you can find these kind of loss coefficients. When you calculate pressure drop in case of flow over a flat plate, it's simple the skin friction drag. And here is shown how you can calculate this skin friction coefficient, and for laminar flow it's this simple function of Reynolds number. For turbulent flow you see a function here, and you can calculate a drag force, which is a function of a skin friction coefficient times this dynamic pressure times the surface area. But if you want to pressure drop, it's simply this skin friction coefficient times this dynamic pressure. That was all this time. Thank you for watching and see you again. Bye bye.